I am Kurula Varghese from Department of Electronic System Engineering, Indian Institute of Science, Bangalore. I am going to give this course on digital systems design with PLDs and FPGAs. As the name suggests, it has something to do with the design of digital systems, and we will be implementing those systems in devices like PLDs and FPGAs. So over the next 40 hours I am planning to complete this course from the basic to advanced portion. But before we start, I want you to do a small exercise. Please take a pen and paper and write what is your idea or expectation of this course. Okay. So basically what do you think this course is about, what is it content, and why are you learning this course? Maybe some people are taking this course to learn the basics of digital design and learn it thoroughly. Maybe somebody is trying to get a job based on this course, or could be somebody else has a similar course in the curriculum and want to complete the course with some good grades. So whatever may be your purpose behind learning this course, please write it down. And the last question I want to ask you is, what do you think should be taught? So from you have some expectation of the course, that is why you have come to this course. So what do you think should be the content of this course? Please write it down. The idea is that in the next few slides I am going to state the objective of this course, what are its major contents, so that you are clear at the outset what you are going to learn by the end of the course. It is not good if I do not tell you at the beginning and you run through the course all the way till the end and realize this is not something what you wanted to learn, then there could be a problem. So when you compare what is the content of the course, what is the objective of the course with your expectation or requirement, and if there is a serious mismatch, you can choose not to attend the course and waste your time. That is a basic idea. So let us move on and let us see what are the content of this course. So mainly the course objective is digital system design. So the main focus is digital system design, by which I mean that somebody gives you a specifications of a system. From that specification, how do you go about implementing the system? Okay. So the system could be a small system like a counter, an arithmetic logic unit, or it could be a microprocessor, or it could be a system on chip, a complex system on chip, whatever. Given the specification, how do you go about implementing this? Having only the knowledge of the specification and the domain, how do you go about implementing it? That is the first objective. When it comes to the next one, say very specific objective, suppose you have an algorithm, say you have a signal processing algorithm for a filter. How do you design an architecture for that filter? And in the parlance of digital VLSI, many a times it is called front end design, and front end means that you, given the specification, from the specification you go all the way to the logic design, that means the design in terms of gates and flip flops. And similar to the front end, there is a back end design which takes these gates and flip flops all the way to transistors and the mask required for the chip or the integrated circuit manufacturing. Okay. So in this course we are mainly concerned with the front end design, not the back end design. So next step is that when you design such a complex system, you have to partition the system into pieces, into blocks, and now you have to take each block and design the blocks in detail meeting the specification of each block, and at least you have to do a timing analysis of each block to be able to work. There are many other analysis you need to do, but at least at a basic level you should be able to make it work in a functional way, and it should meet the basic delay requirement. The third or fourth objective is the device technology. For this course we will be using two device technologies. One is called the programmable logic devices or PLDs. The next one is field programmable gate array or FPGA. So we will be using these devices to implement our design. And the fifth point is that for entering the design, for designing the blocks or designing the system, we will be using a hardware description language called VHDL. We will see what is VHDL later. So the design entry in this course will be using VHDL. There is no particular reason to pick up this language. One could use languages like Verilog, but traditionally the FPGA vendors used to support VHDL more than Verilog, and it is easy to move from VHDL to Verilog than from Verilog to VHDL. So I hope that once you have learned VHDL you can easily switch over to other hardware description languages when required. And I must tell that the main focus is still the digital system design, not the PLDs or FPGA, not the VHDL. We are going to learn this, but the main focus is still the digital system design, not PLD, FPGA, VHDL. We will learn all these thoroughly, but the focus is digital system design. And in the course of the studies we are going to have some few case studies. I will draw examples from communications, embedded systems, computer architecture and all that, these case studies. So I hope you have some basic understanding of these topics. It will help you to understand the course better, and we do not have time for too many case studies. So I hope you have a background in these topics. So that is a course objective, and let us move on. And the next question to ask is, what is the prerequisite for this course, and or what are the basics you should know before embarking on learning this course. And I really assume that you have some background without which this course cannot be learned. So let us see what are the backgrounds required. So essentially you would have gone through some digital systems course or digital circuit course in the undergraduate program. I am not going to cover that part. I really assume that you are thorough with these particular topics. To start with, the Boolean algebra, you should be thorough with the Boolean algebra. Some kind of minimization algorithm, at least you must have done used Karnaugh map for minimizing, and you should have learned gates, the combination logic like the encoders, decoders, multiplexers, demultiplexers, adder, subtractor and things like that, and the sequential circuit like flip flops, registers, counters. All this should be known at the functional level, and you should know the timing parameters of combination logic and the sequential logic. At least you should know what are the delay parameters associated with the gates, associated with the flip flops. Thereafter we can build the complex timing parameters based on this basic timing parameter. And nowadays you know that all the digital circuit is built of CMOS technology or NMOS and PMOS transistors. Maybe in the undergraduate program you would have learned about some other technologies, but that is not important. Currently what is used is CMOS, So if you are not thorough with CMOS circuit, please take some time to learn the basic NMOS, PMOS, the CMOS circuits of various gates and so on. Okay. So the next background I would require is some basics of microprocessors, because when we try to learn design, as an example I will bring in the microprocessor as a case study. So I hope you know some microprocessors like 8085, 8086 or anything you have learned. It could be some microcontrollers like 8051 or a RISC processor as part of your computer architecture. It does not matter. If you know how the processors are designed, what are the blocks in microprocessors, that should suffice. And the next background I require is some basics of computer architecture, basically the arithmetic logic unit, instruction set and so on. So if you have not learned, you can refer to some good books on computer architecture and pick up the basics of the computer architecture. Maybe I am not sure, I will, if required, I will draw some examples from the computer networks or the communication networks. I hope you would have learned at least one course in communication networks. I will try to limit the case studies to first two, but if required maybe I will cite some case studies from these communication networks too. And so these are the prerequisite. If you are not thorough, please take a break, learn this from any textbook, any good textbook, and come back and learn this course. So before getting on to review the basics, I want to state the contents of the course, various parts of the course. This is essentially 5 parts. The main focus will be on advanced digital design. I call it advanced digital design because I assume that you have the background, you know the basics of the digital design. Okay. In this advanced digital design part, we will be mainly concentrating on the top down design or hierarchical design. In particular in a serious digital design there are 2 parts, one is data path and the other is the controller. And the data path talks about the computation, the basic computation. So this is the path where, or the circuit where all the computation happens, and the controller is the one which moves or which controls the data movement within the data path, and there could be one controller or multiple controller. And definitely after this we should be concerned with the timing, that means how to get to meet the timing requirements part of the specification. And there are many other things which when we go ahead with this topic we will see. The next part is the programmable logic devices or PLDs. These are used in a small way for glue logic in digital design, and we will see the architecture of the PLDs, the evolution of this architecture, the application of the PLDs, how to optimally design a circuit using the PLD. The next part will be the field programmable gate arrays or FPGAs, and we will see the architecture of FPGAs, the application of FPGAs and how to optimally design using FPGAs and so on. And the fourth part is this particular language, hardware description language, VHDL. The expansion is VHSIC hardware description language, that means very high speed integrated circuit HDL. And I want to emphasize that we will not be learning all about VHDL. Our focus will be something called synthesis. That means synthesis means that you write a code, you describe the hardware in a language and use a tool to generate the circuit. So our focus will be to write synthesizable code, that means you write some description of a hardware and give it to a tool, synthesis tool. It should be able to generate the circuit that you intend to generate. Okay, that is a basic idea of synthesis. Many a times people write VHDL code which works very well in simulation, but it does not properly synthesize, or it makes no sense as a hardware circuit. So we are not interested in that, this being a hardware design course. So we will be concentrating on synthesis aspect of VHDL. Similarly, this course contains many case studies. We will start with the case studies, minor one, to illustrate the design methodology, design steps and so on, and when we come to the end of the course we will take more complex case studies. So these are the 5 parts of the course, but I am not going to teach it sequentially from say from the top to bottom. I will start with advanced digital design, proceed, come to a logical end, then come back to VHDL to cover the basics of VHDL, then go back to this advanced digital design, then maybe handle these two, complete the remaining VHDL with case studies, and ultimately tie everything together in this part. Okay. So that is the essential course contents. By now I think you should have some clear idea what this course is going to be, but definitely that is a content. I cannot talk about the way in which I am going to handle these topics, which could be a little different, which you have to wait and see my treatment of this particular subject. So next in few slides I would illustrate, or I will say what I am expecting you to achieve at the end of the course. So, or what competencies you will be hoping to develop, or I expect you to develop at the end of the course. So at a system level I expect that you will be able to design a digital system given the specification, meeting the essential functional timing requirements or constraints. You should be able to do that. In particular, if you have an algorithm, you will be able to design an architecture with the data path and controller with all the issues related to it sorted out. So let us look at each module level. So with regard to digital systems itself, you will be able to design the data path and the controller using the high level combinational and sequential blocks. Okay. What I mean by higher level combinational and sequential blocks is that when you design in your undergraduate courses something like say a full adder, you will use some gates. When you design a counter, you will use some flip flops and few gates, and you literally start with the truth table, work out the Boolean equation, minimize it and implement it with gates and flip flops. But when you design a complex system, we will not be able to do it at the flip flop and gate level. We are going to use the non combination blocks like encoder, decoder, multiplexer, demultiplexer, adder, subtractor, and sequential blocks like registers, counters and so on. Okay. So that is what I mean by higher level combination and sequential blocks, and you will be able to solve the functional and timing problems in the data path. Many a times with your background maybe you are able to solve some functional problems but not the timing problems. So we will concentrate in this course quite a lot on the timing aspect of the digital design. Basically at the end of the course I hope you will be able to think timing. Okay. Many a times people are able to think functional aspects, but I want you to think the timing aspects too, to develop that capability. And when you design a controller or finite state machine, there are various issues, functional and timing issues, and you should be able to solve that. And the last point is that when you have a digital system, you may have different parts of the digital system working with different clocks, and or there may be a part of the system working with one clock, and you will receive some manual input from a limit switch or a keyboard to the system, and unless this is handled carefully, because an event happening in with regard to one clock or one manual process reaches the another part, unless it is synchronized to the receiving domain's clock, this won't be registered properly. So that is called synchronization aspect, and that we will at least the basics of synchronization will be taught in the course. I may not have time to teach the synchronization issues in very detail in this course, but I will make sure that the essential synchronization will be handled in the course. So let us move on to the VHDL. The VHDL part, at the end of the course you will have the competency, given a block, given a design, you will be able to write a synthesizable VHDL code to implement this block. And in the reverse way, suppose you have a VHDL code given to you, then you should be able to infer what is the circuit that this particular code implements, or given this code to a synthesis tool, what probable circuit the synthesis tool will generate. Many times this is required because you will be working in a project team. You may have to handle the code written by another designer who has worked earlier on the project, and unless you are able to infer the functionality of the VHDL code, you will not be able to proceed. So this is a competency which is required. And we will also learn how the VHDL simulator or simulation tool simulate the code. Why this is important is that you know that the language is a sequential language, but the hardware is concurrent. Suppose you have say 5 outputs from some 10 inputs in a combination circuit. Any one of the input changes, all the 5 output can change, but in a language when you write 5 outputs, it has to be written one after the other. But when you simulate the functionality of this 10 input 5 output system, everything has to happen. Suppose at 100 nanosecond one of the input changes, say after some time all the output should change. So we will learn how the simulation tool handle the concurrency and from a sequentially written statement. It is not very complex, but it is for our understanding, that is not for us to break the head, it is for the simulation tool to do all that what is necessary, but a clarity in understanding is important. And in a complex system you cannot manually verify or manually simulate and verify the circuit, we have to automate it. So we will in VHDL, these are called test benches, that you can automate the whole verification process. So we will learn how to write test benches in VHDL. So this is the competency I hope you will develop at the end of the course with regard to VHDL. So let us move on to the next topic, PLD. So at the end of the course with regard to PLDs, I hope you will be able to choose a particular PLD for a particular application. This in the case of PLD it may not be very complicated, but still you wouldn't at least choose a PLD which is too small to accommodate the design, or you may not spend too much money in choosing a complex PLD, very complex PLD for a smaller application and so on. And you will be able to design and code to exploit the architecture features of PLD. We will learn the architecture features of PLD, and we will learn how to design properly so that those features of PLDs are best used in our design, so that the resources are not wasted or we get the required timing performance. So these are the competencies you will develop at the end of the course. So let us move on to FPGAs. With regard to FPGAs, once again you will be able to choose a particular FPGA for a particular application, and as in PLDs you will be able to use the architecture features of FPGA to design and fit a particular design within an FPGA, and you will be able to design to meet the area and delay constraints and estimate the power consumption of your implementation within FPGA. So there are these are little more elaborate than the PLDs, and these devices are complex, more complex than the PLDs. So these are the competencies with regard to the digital system design, VHDL, FPGAs and PLDs. I hope you will be able to develop at the end of the course. So now I want to in the course of the lectures I will be suggesting some exercise for you to work offhand, and this will cover the various aspects covered in the course and basically deal with the concept. Many times students are little worried about the textbook kind of simple exercises, but you have to trust me, it is very important to do exercises which bring clarity to the concept. Okay. Many times people are in a hurry to design the real life systems, but unless the concept is clear you will not be able to sort out the problems you encounter, come out with elegant design and creative designs and so on. So it is very important to work with exercises which bring clarity to the concept than some gimmick. So we can do all gimmicks, you know, up LEDs or bringing some LCD display with some text and all that. That is basically sometimes it's a gimmick or it impresses people, but it may not enhance the learning or enrich your understanding. So I will be giving exercises or telling you to do some exercises which bring clarity, and I will suggest some mini project towards the end of the course so that you can try to apply what you have learned in the subject to sort out some issues in a small case studies. And for these exercises you can use the free web editions of the PLD and FPGA tools from major FPGA and PLD vendors like Xilinx, Altera, Atmel, Lattice, etc. And if possible you can try to get some PLD FPGA kits which are low cost and try to implement some of the exercises we discussed on this FPGA kits. So these are the points I want to tell you about the exercise. So let us move on to the last part of the introduction. These are the references. So these are some of the references, but I will not be using any of these references very thoroughly. I will be using my own notes, my own slides and my own way of handling the subject, but these are very good books. The Walkerley digital design, it's a very good book. So even for the basics in digital design you can use the same book. Suppose if you are not thorough with the basic in digital design you can use this book to learn the basics in digital design. VHDL for Programmable Logic by Kevin Cahill. This is a good book for VHDL for synthesis, little bit old but very good book. You could use any book which handles the VHDL for synthesis. Then the VHDL book by Nawabi, it's a kind of complete bible, and then for CMOS circuit you can use Westy, Harris and Banerjee's book on CMOS VLSI design. There is a book by Charles Roth, it's a very good book on digital design, I have not listed here, and I will be referring to various literature in this field and FPGA PLD data sheets. So you can refer to them also, I will say whenever I use these references. So this gives an introduction to the course. Basically I have told what is the focus of the course, what is the objective of the course, what is the content of the 5 contents of the course, and the competencies I hope you will develop at the end of the course at a system level and in each part, that is what I have told, and the reference books. So this is the basic introduction to the course. Now we will take some time to review the basics which you have already learned, which I assume you have, but I will run through give an overview of the field and run through some basics, not thoroughly. It will be a quick maybe 1 or 2 hours of lectures on the basics, then we will move on to the real digital system design. So let us look at a digital system design with PLDs and FPGAs, an overview. So I want to you to have some clarity about learning and design. In learning you always go bottom up. That means see, normally you start with transistors like CMOS, NMOS transistor, PMOS transistor, CMOS transistor and so on. Then after having learned quite a bit about transistor, you learn how to build gates based on this particular transistor, say AND gates, NAND gates, OR gates, NOR gates, inverters and so on. Then you will learn how to build combinational circuit based on these gates, okay. Then build sequential circuit like the controllers or the data path or registers with combinational circuit, all that you will learn. Then ultimately you will learn how to interconnect all these in a system. So when you learn, you go from the smallest pieces to the complex system. But when you design, it is the opposite process we adopt. We go top down. Suppose you want to design a microprocessor, then you break the processor into pieces like ALU, registers, say program counter, stack pointer and so on, okay. Then you take one of the piece, say you take ALU and break down into adder, subtractor and so on, and then you pick one of the pieces from that and the adder is converted design in terms of XOR gates, AND gates and OR gates, and ultimately these gates are converted to CMOS transistors. So the hierarchy in design is always top down. So anything complex you should try to do top down, okay. Suppose you take an aircraft, you cannot start with somebody designing a wing, somebody designing a fuselage and somebody designing an engine and ultimately bring it together, fit it together without any idea of the aircraft, okay. So anything complex, maybe it is true with the software. Suppose you have a complex software, you cannot arbitrarily design pieces and put it together, or you organize a function, a conference. So you cannot, you have to have a global view, say somebody will handle the program, somebody will handle the stay arrangement, somebody will handle the finance, somebody will handle the travel and so on, okay. So anything complex should be handled in a top down manner, but learning should be always going from the basic to the complex, okay. So I am going to illustrate that in picture to bring some clarity to it, okay. So let us move on to this. So say at the when you learn at the basic level, I call it level 0, you will learn about the MOS transistor. Say you pick up this NMOS transistor, then you know that there is a P type silicon, N type source and drain, then polysilicon gate, source and drain. In the PMOS it is opposite, you have the substrate is of N type and the source and drain is of P type. Then you know, you learn the IDS, VDS characteristics, what are how the IDS change with regard to VDS and for various VGS and so on, and you learn various regions, you know, you have the linear region, saturation region, cutoff, and you learn sometimes some symbol. So this is the symbol for an NMOS. You have a drain, source and a gate, and when the gate is at a higher voltage with regard to source, it conducts, and for the PMOS when the gate is at a higher voltage with respect to source, then again it conducts. Normally it is opposite voltage we apply, and we know that, and then NMOS is a good conductor of 0 and PMOS is a good conductor of 1. Having learned this MOS transistor, then you move on to the gates. So take the case of an AND gate. AND gate is designed using PMOS and NMOS transistor. So if you look, if you have learned this part is a NAND gate and this part is an inverter. So this is a NAND gate followed with an inverter. So you can see that if A and B are 1, these two transistors will be off, this will be on. So this essentially connect this point to the ground, so which inverts it. So if both are 1 1 you get 0. So any of the input is 0, then you can see one of the transistor will not be conducting, so this path will be off and one of these transistors will be conducting. So you will get a high here, so accordingly you will get a low there. So and that is the symbol of a gate. Similarly you have like AND gate, you have NAND or NOR, XOR gate and the inverter. So in the level 1, having learned the transistor, you learn about the gates, what are the input output relation in terms of the binary values this gate implements. Now once you know the gate, you are able to go to the next level, level 2. Say take the case of a full adder. The full adder has a 3 input AB, 2 bits and a carry input normally from a previous stage, which gives a sum and the carry out, which you can use it in the next stage. So this is a full adder is a modular adder slice which can be combined to form bigger adders. So this is the truth table, and you know that if any one of the input is 1, sum is 1, any 2 are 1 then the sum is 0 and the carry is 1, all the 3 are 1 then both are 1. Okay, this you have studied, and if you work out minimize, then you will end up with this expression. So this is the next level. In the level 3 you move from the full adder to say a 4 bit ripple adder. So using 4 full adders we are building a 4 bit ripple adder. This is the A0, B0, the least significant bit of the inputs. A3, B3 are the most significant bits of the inputs, and these are the sum. This is the carry into the first stage, this is a carry out of the next stage is connected as a carry input to the next stage and so on. So knowing the full adder we will be able to build a ripple adder at the next level. So we go further, maybe you go to a multiplier. So this is how the architecture of a multiplier looks. So if you care to look at the multiplication algorithm, the paper pencil method, say here we are putting a 5 bit multiplicand and a 5 bit multiplier. For each bit of the multiplier you form the partial products, and you know that when it comes to the second bit this is the power of 2 raised to 1. So the partial product is shifted. If the bit is 0, the 0 is shifted. So ultimately you form the 5 partial products and you add it together, you get the product, but then it involves a lot of adders. So in a realistic design, to save the area we use a single adder and form the first partial product, add to the accumulator which is 0, then form the next partial product, add it. So here you have an accumulator, you have a multiplicand, you have a multiplier. Okay. So look at the least significant bit of the multiplier. If it is 1, initially the accumulator is 0, you add the multiplicand to it, then you instead of shifting the partial product left you shift the accumulator right, and then this the least significant bit of the multiplier is gone. The next bit comes here. So you look at it, if it is 0 you recirculate, you take this result itself, put it back and shift it, because it is equivalent to adding the 0. Instead of adding 0 we take this and put it back and so on. Say do this 5 times, then you will get the desired result. So which involves 3 registers and an adder and some control which is not shown here. So we can say this is the data path of a multiplier, which basically use our idea of the adder. Okay. So that is how the learning happens. You started with the transistor, then move on to the gate, then we have moved on to the full adder, then we made the ripple adder, then having some idea of the flip flops you are able to build a multiplier, or you are able to understand the functioning of a multiplier very thoroughly. But when you design, so let us look at the design, how to design this multiplier. You do the opposite. So knowing the algorithm of the multiplier, you design an architecture for the data path of the multiplier consisting of 3 registers and an adder. Now we have to design this adder and the registers in a detailed way. So let us pick for example the adder, say assume that is a 4-bit adder, 4-bit multiplier, then we will design this 4-bit adder with 4 full adders cascader. So the adder is broken down into 4 full adders. Now you take the full adder and design using gates, using XOR gates and 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 OR gates. So this is a majority logic, any 2 or more than 1 input is 1, then the carry out will be 1. Now the moment you do that, we know all the gates and then go to transistors, and ultimately the chip masks are built from the transistor layout that is not shown in the picture. So up to here, from here to here to here is the front end design, that from the spec, the multiplier algorithm, we have come to the gates and the flip flops. In this case there are no flip flops shown, but you know essentially a register is composed of flip flops. Suppose a 4-bit register is nothing but 4 flip flops in parallel, and so this is very easily designed as 4 flip flops in parallel. So this is how the design proceed in a top down approach, and of course you should have the domain knowledge to design. You should know all the pieces. It is very important that you are thorough with all the building blocks so that you will be able to design it thoroughly, and you should be able to sort out the problems as you encounter as you design. Okay. So this shows a hierarchy of learning and hierarchy of design. So let us move on. So let us ask what are the major constituents of a design. That means suppose somebody tells you to design a multiplier, what should we focus on? Okay. And many a times students, the smart students say it should be low power, it should be low area, it should work at 1 gigahertz frequency or high clock frequency and so on. Okay. But think for a moment, you design a multiplier and you say it works at 1 gigahertz, but given some input, say you give to the multiplier 7 and 5 and it gives an output like 42, but you say it works at 1 gigahertz, it is of no use. Okay. Or you say it works, it consumes hardly any power, only microwatts, but the answer is wrong, then it is of no use. So that tells you that the primary part which we have to focus on is the function or the logic. Okay. So when you design, the first part or the first constituent, the first focus should be on function and logic. The power, area, timing, everything comes later. Okay. The first will be function and logic, and you are lucky in this way because you would have learned all the building blocks in a basic course, and I will list, there are 2 parts, combination logic and the sequential logic. So the combination logic, you would have learned all these, you would have learned Boolean algebra, you would have learned minimization, some algorithm like Karnaugh map and things like that. You would have learned various functions like AND, NAND, OR, NOR, XOR, inverters, the gates implementing these functions, something called encoders and decoders, multiplexers and demultiplexers, parity circuit, comparators, priority encoder, open drain outputs, tri-state outputs, Schmitt triggers, adder, subtractor, increment, decrement and so on. So we are going to use all of these. Okay. Some may not be explicitly, like we may not do any minimization, most of the time this is done by the tool in a higher level design, but an understanding of this is very much required to grasp the concept and bring clarity into the whole game. And so all these are very important, what are these composed of, how these are designed and so on. So let us move on to the sequential logic. When we come to the sequential circuit, the basic building block is the flip flops, various type of flip flops, like you would have learned D flip flop, SR flip flops, JK flip flops, T flip flops, and latches, and there is a difference between latch and the flip flops. Latches are by definition transparent. When the clock is high, the input output follows the input, and when the clock is inactive, the last input is latched onto the output. In a flip flop, normally works on the clock edge. When a active clock edge comes, the input is transferred to the output, provided some input meets some timing requirement, we will see that. And you would have learned some kind of counters like ripple counter, synchronous counter. A ripple counter is of no great interest to us, so forget about it. We will be talking about synchronous counters, various registers, parallel registers, shift registers and so on. And the finite state machines, I am not sure whether you have learned this in the basic course, but we will I assume that you may not have learned, and we will put some time developing the concept and the design of finite state machine. And various memories are important, various kinds of ROM, read only memories, erasable programmable read only memories or electrically erasable prompts. Similarly static RAMs, these are fast memories which is used in a computer system at the level 1 as caches and level 2 caches and all that. Synchronous SRAM, nowadays everything is synchronous with the clock. DRAMs is the secondary level of storage in a computer system. These have the large capacity, but it is not as fast as SRAM. And you have FIFOs, which is first in first out memory. That means you have 2 ports, on one port you write and one port you read. Many times the addressing is implicit, that means you do not specify the address. The first data you write will go to the first location, and the second you write go to the second location, and when a circuit read the output, it reads starting with the first, and the read pointers and write pointers are incremented depending on the read, and one has to take care that one does not overtake the other and so on, okay, that there is no overflow or underflow. Similarly CAM, normally it is defined as an opposite of a memory. Here you have data stored in a memory and you search for some content, that means you provide data, it says the location where that particular data is stored. So in a normal memory you provide the address, you get the data, but here you give a data, then you get the address which is used in the cache memories, and all search algorithm, lookup algorithm use CAM for its implementation. So this is the major constituent of digital design, that is combinational logic and sequential circuit. And if you care to look at a data sheet maybe of a gate or a PLD or a microprocessor, the first thing in a data sheet stated is the function of that integrated circuit. So that shows the priority, the function as over other factors. So we have little time left, let us move on to the with some of the blocks we have discussed. I am not going to deal with all the blocks, let us pick up some of these combinational blocks and just revise so that it brush up your memory. So let us move on. So with regard to minimization, all of you must have learned Karnaugh maps, okay. This is a very systematic method of minimizing from the min terms to minimal product terms, and this is a graphical tool. It is for humans to work out, it is not for computer to work out. The equivalent computer algorithm is called Quine-McCluskey. As in Karnaugh map, it provides a minimal solution, but the complexity is very high. It has exponential complexity because it starts with the min term. Suppose you have 5 variable problem like A, B, C, D, E, and you already give an expression to Quine-McCluskey like AB bar, you know that it expand in terms of the 5 variable. So already minimized expression is taken back to get the absolute minimal or optimal the product terms, okay. That is the idea of Quine-McCluskey, but you know that given an n input that you have 2 raised to n min terms, so the complexity is exponential and is very hard to compute using the Cohen-Mikulski. So mostly the tools use a heuristic algorithm called espresso. This is based on Cohen-Mikulski but is faster. So that means if it has a product term already which is simplified, is not going to expand all the way to the min terms and start reworking back. So but since it uses some kind of heuristic method or shortcuts, it is not going to produce an exact optimal or minimal solution as in Cohen-Mikulski, but it will give a near minimal solution, and we do not care because many times we are not worried about the area so much nowadays. Like it does not matter, instead of ending up with say 25 product terms, you might end up with 27 or 30 product terms. It should be okay in the present technology. So these tools will use espresso kind of heuristic base the tools for minimization or algorithms for minimization. And the next thing you should realize a little bit about the real life is that all these applies many a times to the 2 level implementation that you talk about, and or and or sum of product or product of sum, which you have learned in your the undergraduate program or the basic course. But in real life when you come choose the FPGAs or ASIC, you do not stick to the 2 level implementation because it is not possible. So you will have to implement a particular circuit in multiple levels of logic. So you will have to apply some decomposition of a Boolean expression or a circuit into multiple terms so that multiple levels can be implemented. And suppose when you have a multiple output, suppose you have 10 inputs and 5 outputs, then you will have to for a minimal expression in terms for the multiple output, you will have to find the common sub expression like maximal common sub expression of all the multiple output. So you need algorithm to find the common sub expressions across the multiple output which minimizes the area, and many a times this involves the steps like the factoring, substitution, flattening etc. for the multi-level implementation of the digital logic. So the minimization is more complex than you have learned. It uses heuristic algorithm and it concentrates on the multiple output minimization and multi-level minimization and so on. So these are complex. Those who are interested can look at the synthesis of digital circuit. These are that is a subject which looks at this minimization algorithm. So let us move on. So let us look at this part, functions and gates. I just want to tell you that you would have most of the time you confuse the gates with the function, okay. So you take an AND gate, then this AND gate you take it to implement the AND function, but many a times the AND gate can implement many other function than the AND gates AND function. So let us look at the truth table of an AND gate. Say like in an AND gate, when both the inputs are 1, the output is 1, that means A and B are 1, the output is 1 in the case of AND gate. So here we are treating the inputs are active high and the output is active high. So then the AND gate implements an AND function, but if you treat the AND gate inputs and outputs are active low, look at the truth table. If A, B are active low, and look at the truth table, if any of the input is active, any one of the input is active, then the output is active, which is nothing but an OR function. So if for the same AND gate, if you treat the inputs and outputs are active low, then implements an AND OR function. So that is shown as an OR gate with showing the active levels. So AND gate can implement OR function when the inputs and outputs are active low, and if for a a smart student you can easily know that this is nothing but applying the De Morgan theorem. So y is AB, and if you take y bar is nothing but AB all bar, which is nothing but A bar or B bar. So I am showing bar by a slash because I can use the text for that. So that is shown here. So an AND gate can implement AND function or OR function, and which is basically applying the De Morgan theorem or building the De Morgan theorem into the concept. Okay. So in the next lecture we will continue with this. So today in the second part of the course handle, basically we have looked at the major constituents of a design, that is function. Basically what all you have learned in the basic undergraduate course, the combinational logic, the sequential logic, all that is important. Then we have looked at the functions and gates. Before that we have looked at the minimization, the multi-level multi-output minimization and the algorithm used for that. So in the next lecture we will continue with this function. Maybe in next 1 or 2 lecture I will be able to cover the complete the basics needed, run through the basics. Then I will also give certain the current state of the art in this particular field to give you an idea, an overview. Thereafter we will start with the main focus, the real digital design, showing the example how to go about designing and the concept. I hope you enjoyed this session. Please go back and work on the basics I have covered. Those who have not learned the basics, please go back to the reference book, learn the first few chapters covering the combinational sequential logic, learn bit about microprocessor, learn bit about the computer architecture, so that when we move ahead you are in sync. I wish you all the best and thank you.